So, good morning to all. We will continue thermal analysis aspect where we stopped in the last lecture. Right. So, we have discussed and covered various topics as you seen in the red color thing, and currently we are discussing about the thermal analysis. In thermal analysis, we have discussed about the break energy and discussing about the breaking power aspect, and further we will discuss about the break power absorbed by lining and the drum, and also we will discuss about temperature analysis in single stop breaking. Okay. So, these are the three information we are going to learn from today's lecture, and we'll give a recap what we have discussed in the last lecture regarding the brake power. So, when vehicle moves on the level road, right, on the level road, when apply brake, the vehicle decelerates. When a vehicle decelerates, the energy, the brake energy what we got, right, the average brake energy BP, right. So, hope you remember this is Km, right, Km 2G W A V1. This is what we got. This is for a level road. For level road, right? Just braking, single stop braking, kind of just braking aspect. I am sure you know that the Km is the correction factor, right? Correction factor for rotating masses, right? Rotating mass, yeah, right. And W is the vehicle weight, vehicle weight, weight of vehicle, that is fine. And V1 is the initial velocity, okay, and A is a deceleration rate, deceleration, that is fine, yeah. So, now the question is, what happened when the vehicle moves in the downhill? How would be the brake energy, right? That is what we are going to discuss as a second case, case 2. Downhill, or else what do you call drag braking, right? Drag braking or continued braking, okay. So, assuming that the vehicle moves in a slope, I am just wanted to show like this, yeah. The height, you take it as a h, this is the height, okay, of the thing, and theta is the slope, theta is the slope, okay. Initially the vehicle at this position, just to show the things, moving velocity V1, right, moving velocity V1, and it moves, it will cover maybe dl distance, delta L, with the velocity when you are applying the brake and V2. So, this is what happens, okay. So, in fact, you can even take the slope. When you take the slope, this will be your dh and this is your dl, is nothing but your theta gradient. When I discuss about during the gearbox, particularly automobile gearbox, we have discussed about the resistance, hope you remember. So, air resistance, rolling resistance and also gradient, right. This is nothing but when the vehicle moving from in the on the slope from top to down, that is why it is called downhill. So, everything boils down to your the gradient theta aspect, okay. So, so what is the general equation here? So, when the vehicle is moving from here this position at a velocity V1, you are applying a brake. What is the purpose of brake here in the slope? You have to maintain the vehicle velocity same, right, that is the purpose, otherwise it will be the movement will be uncontrolled, you need to make a control, okay. So, usually you will have two equations, right, the brake energy EB, right, km 2gw v1 square v2 square. So this is the kinetic energy. Anything else do you expect? Anything else when the vehicle moves downhill? It's moving, right? Potential energy also will come into the picture, right? The potential is nothing but from the vehicle weight and the height. So this is your kinetic energy and this is your potential energy. Okay. But generally the purpose during the downhill, you have to maintain the velocity constant to move down, right? So when velocity equal v1 equal to v2 during brake, right? So what happened to this term? The EB, the kinetic energy will be 0, then you will have only WH. That's what is given. So this only will be responsible for your brake energy, right? So now we need to find out what would be the brake power, right? So what would be the brake power, right? Yeah, the brake power nothing but dt. Okay. So EB already we know that WH and dt, but I want to know that just since it's moving in the slope, I simply multiply both numerator and denominator with the dH by dH. So when you rearrange dH, okay, I think this should be dH and this will be dH by dt. This one is there. Okay, fine. So what will be the dH by dt? The rate of change of height with respect to time. What do you call it? It's a velocity, right? That's a vehicle velocity. That's one aspect. The other aspect, from this diagram, what do you understand dH by dl? What is the dH by dl? Nothing but sin theta, right? Yeah, sin theta is a gradient. It's a gradient. So sin theta, right, or g is the gradient. Normally the gradient represent with respect to percentage, 5%, 10%, 15%. In fact, in the velocity profile, during the what do you call it, brake effective forces aspect, right? We have discussed thing. In fact, if you rearrange this, finally the brake power, right, so will be finally down to your vehicle weight, velocity and the sin theta. So this is what happening. Okay, the sin theta is nothing but is the g is called road gradient. Normally is indicated into percentage. Usually it will vary from 5% to 20%, depends on the slope, depends on the how steep the slope. This is what happened. So in fact, you can rewrite this brake power, average brake power, WVG is the for when the vehicle moves on the downhill aspect. Okay. So this is the standard equation. In fact, yeah, maybe I will move another equation. Have you heard about slip? Are you familiar with the slip? What do you understand slip? Slip, what do you understand? You are not considering the slip anything at the moment. Okay. So what happened when you taken care of the slip? What do you expect? Okay. That one question. What about the rolling resistance? What happened rolling resistance during the downhill? Do you have to overcome or do we need to take care of that also? We have to take care of, right? Because we are moving against the rolling resistance, that is also you need to take care of. So in fact, right, so when you do that, this is what happening. So you can see that the same equation, what we earlier EB is nothing but your the brake power BP, right, BP or So brake power we talk about. In fact, we talk about like in terms of heat transfer. All are same. Please understand that as a Q. So what we got, WV sin theta or else WVG is taken. Okay, that is the gradient. But within the gradient, you have to move against the rolling resistance. So when you do that, then the equation modified Q equal to VW G minus mu r. I am sure you know what is the mu r. Mu r nothing but your coefficient of rolling resistance. Typically mu r vary from 0.01 to 0.03. So this is the standard value you will expect for rolling resistance aspects. Okay. Now there is one more thing I want to introduce. So far we have never taken care of the slip, assuming that the slip is 0. Okay. So but actually you will have you will experience slip. Let me ask question, what do you mean by slip? There is a definition given, time slip defined by the ratio of the difference between vehicle forward speed and circumferential speed to the vehicle forward speed. There are two things are there. Okay. Assuming that you have 2 gears, right? Assuming that you have 2 gears. So whatever the speed is giving by the input, the same speed, if they are same size, the same speed you would expect, right? So assuming that if I give you 100 RPM, my input gear, the output gear also should give you 100 RPM. Instead of that, if it gives 96 RPM, what do you think? It's reducing the speed. So there is a slip. So that is called negative slip. 4% is reduced. That's negative slip. Okay. Instead of 100 RPM, the output gear rotate 104 RPM. So what happened that one? So the difference should be 4 RPM, right? That is the slip, which is a 4%, which is a positive slip. Both ways there. Positive slip and negative slip is there. So the physical meaning is, so whatever the energy when the vehicle is moving on the level surface, when you apply a brake, right? So the friction energy developed. The entire friction energy is developed from the road and the tire interface should absorbed by the brake, right? All the energy, whatever the energy is generated by the tire and the road interface, that should be transferred completely to your brake thing, right? Then the case the slip will be 0. The slip will be 0. So let me ask question, assuming that you have a 100% slip, what happened then? The energy never transferred to brake. Whatever the energy is coming from the interface of the road and the tire won't transfer to your brake, won't absorb by the brake. So we have to incorporate the slip also. That's the reason the same equation is modified with respect to the slip accident 1 minus s. The s is given in the slip, usually will give you in terms of percentage wise. Slip will be given in terms of percentage wise. Okay. So now we understand about the power aspect, right? We understand about the power when the vehicle moves on the level road and the vehicle moves on the downhill. Okay. Now we will move on to what happened, how this power absorbed by the your brake lining on the drum, right? That we need to understand. And also, is it possible to measure the temperature of brake, I am talking brake lining and drum or rotor? Is it possible to accurately measure? Is there any technique? Do you think so? Any techniques are available? Of course, you can have thermal cameras, right? That will give you the localized exact temperature. Other than that, it's difficult. So we have to go for some other way to identify, to understand how much heat is absorbed by the lining as well as drum. That's what we are going to discuss, the heat transfer aspect. Okay. So breaking power absorbed by lining and drum. Okay. So when we discussed, so I need to give a simple information for your understanding. So when you talk about the power, right, BP or else Q or else heat transfer, we indicate the same thing, right. That's please understand that. So when we talk about the heat transfer between the lining and drum, right, or between the lining and the rotor, they are same. Drum and rotors are same. Whatever the analysis we are going to do between the brake lining and the or rotor or drum, they are same. It's valid. Okay, please understand that. So when you talk about rotor or disc or drum, they are same, right. So they are same. That's one thing I need to say that. So, so entire analysis it's applicable to, they are interchangeable, motor or disc same thing, right. That's one thing is there for disc brake aspect, whereas drum is for the drum base aspect. Okay. And one more thing is, since we can't identify the temperature directly, we have to go for another method called thermal resistance. We will approach all the analysis through thermal resistance aspect. Okay. So when you have thermal resistance, what do you understand? This is heat transfer. The thermal resistance always reciprocal to your thermal heat transfer, right? Your basic, the sigma RH, RTH. This is called thermal resistance. Okay. 1 by summation of thermal resistance, right. So in fact, this thermal resistance depends upon the material property. Thermal resistance of the brake or drum or rotor depends on the material properties. Okay, what else we can say? The size. What is the size of a drum? What is the size of your disc? The size. Any other properties? The thermal resistance depends on the material properties, size and thermal property. When you talk about thermal properties, what are the properties? We talk about your thermal conductivity K, thermal conductivity, right. Then your density, okay, specific heat capacity. What else you have? Thermal conductivity, density, specific heat capacity, and one more term is heat transfer coefficient. Right, these are the thermal properties. These are the thermal properties. So for steady state condition, we would like to find out what is the heat transfer between the rotor and pad. Okay, QR is a heat transfer rate of the rotor. Q means the heat transfer of the pad. So since we said it's a reciprocate, this should be RP, right, and this should be summation of RR. Okay. So I just wanted to emphasize QR equal to heat transfer into rotor or drum, that should be watt per meter square in surface area. QP is the heat transfer into pad, right, that is also watt per meter square. Then the sigma RP, thermal resistance right, to conduct heat into pad, right. This is the pad. So normally this is a Kelvin per watt. Okay, this is Kelvin per watt. Then this is R, the same thing, thermal resistance to conduct heat transfer, okay, into rotor or drum. That should be Kelvin per watt. So, this is the units. Okay. So, this is the concept we are going to apply, right. This is concept we are going to apply. Remember, the braking happens in what is the way, either single stop braking, repeated braking, or continued or drag braking. So, okay. So, we are going for the single stop braking. So, what do you understand single stop braking? For single stop braking, what do you understand? Okay. Do you expect any for single stop braking? For single stop braking, you are allowing the vehicle to reach the maximum speed and apply a brake, right. So, by doing that, so what happened, there is no time for the cooling aspect, there is no time for the cooling aspect, okay. Because of the time is, the braking time is smaller. When the braking time is smaller, even the heat transfer to the braking will be lesser. That is what we have discussed in the last lecture, okay. So, so in that case, what do we understand? We will take it as the braking line and the brake lining, right, and the rotor or drum as a semi infinite solid. These are basic your heat transfer, semi infinite solids, right, and there is no cooling, obviously no cooling takes place between them, right. So, what happened then? There is no cooling. So, obviously what happened to temperature, right, tell me what will be the happen temperature, yeah. Okay, it will increase the high temperature, oh fine, but I am talking about there is no cooling, there is no cooling, because of you are allowing the system to absorb the things, right. So, allowing the system to absorb. So, to have an identical temperature between the brake lining and drums interface, when do you expect the identical temperature? Right, whatever the heat absorbed or generated must be equal to heat absorbed, right. With that, in that condition only the temperature would be identical for the both brake lining and the drum, okay. So, the reason is I need to identify how much heat is absorbed by the drum, how much heat is absorbed by the brake lining. I had to find it individually, right. So, the only way is I had to find out the heat transfer through the thermal resistance, since the temperature is not known accurately, right, okay. So, to have identical, okay, I am making as equilibrium identical temperature between the brake lining and drum brake lining and drum interface the heat transfer or heat energy generation must be equivalent to heat absorption, right. This is what happened. So, heat energy, whatever the heat energy it generated must be equal to heat absorption. So, in fact, if I want to identify the individual heat transfer of the rotor and heat transfer of the pad, right, already we given your heat transfer is reciprocal of sigma RTH, right. So, I want to identify for the heat transfer of the rotor, that depends upon what, your density, right, yeah, right, your density. What else we have? Density, specific is capacity and K. Have you heard about thermal diffusivity? Right, it depends on the how much the thermal deficit. Thermal deficit again it depends upon the your density, thermal conductivity as well as specific heat capacity. Okay. So, this is rho RR, CR, right, KR, and this will be pad, rho pad, C pad and K pad of thing. So, this is what you are getting. In fact, just give you the information, the suffix R indicate about the rotor or drum, the suffix R, whereas suffix P indicate about the pad, okay, where rho is the density, C is specific heat capacity, okay, and K equal to thermal conductivity. Of the material. Okay, this is the thermal conductivity of the material. I want to identify totally how individual heat transfer takes place between the lining and the drum aspect. In fact, I need to identify the heat distribution factor. Okay, dF, right, the dF individually for the rotor as well as for the drum also, rotor and the brake line, sorry, yeah. Right. Before proceeding, I just want, this is the your total heat transfer Q would be the summation of heat transfer of the rotor and the heat transfer of your pad, right. These two will give you, right. So, we want, when you say talking about the distribution factor, among the 100% how much heat is going to the rotor that or to the lining, that is the way we are going to do that. Okay. So, when we talk about for the heat distribution factor for the rotor QR, okay, heat distribution factor dF equal to QR by QP, yeah. So, if we rewrite 1 plus QP by QR, right. This is a total heat and this is the only for the rotor element. So, they will give you proportion, what will be the heat distribution factor for the rotor or drum alone. Okay. Now, already we know the QP and QR aspect. If we substitute, then finally we expect the heat distribution factor of rotor dF 1 by 1 plus rho P Cp Kp divided by rho R Cr and Kr of square. So, this is the equation. So, similar way you can find out the brake lining also, right. Yeah, you can same way you can do the brake lining also. Now, that is for the single stop. Okay. Now, we need to understand the brake power absorbed by the lining and drum, right, for the repeated braking. In single stop braking, there is no heat cooling aspect, whatever the energy is developed or generated is fully absorbed by the drum and lining. Okay. So, let me ask question, what do you mean by repeated braking? What do you understand repeated braking? Okay. Assuming that this is your the time and this is the velocity, right, of the vehicle. So, normally you have to accelerate to the one particular speed, maybe you can say is V2, then another speed is V1. Okay. So, you have to accelerate at particular speed, apply a brake, bring down to the velocity to the lower velocity, right, again accelerate, decelerate, right, accelerate and decelerate. So, this phenomena is called repeated braking, yeah, this phenomena called repeated braking. So, in this phenomena would you expect any heat, any cooling aspect? Obviously, you expect the cooling. So, we have to consider the cooling. Earlier it was very easy, whatever the heat generated, it is absorbed by the brake lining as well as the drum, whereas that is not case, you have to account for the cooling also. Okay. So, in fact, I will just write a schematic diagram, just since we are talking about the disc brake at the moment, the symmetry aspect I am giving you only half of the tuck. Okay. So, this is the symmetry, right. So, assuming that this is the, I take half of the rotor or drum, either way is fine, half of rotor. Okay. I take it as a, this is the length L, this is the length L. Okay. Then you have a brake lining, this is my brake lining, this is the brake lining. You expect brake lining just like that, or you expect anything support also? There should be some metallic support also will be there. So, that will be another thin plate is going to be there. There is a thin plate is there. So, tell me how will be the heat transfer takes place in the system. So, I have given the drum. So, this is just the half of the things. What do you expect? So, this is your rotor and this is your pad and this is your pad support. This normally is a steel, pad support is a steel or some metal it is given. Okay. Tell me what are the you expect here, what are the things? Do not you expect convective heat transfer, right, on the rotor, right? You expect the convective heat transfer. What else? The disk QR. What else you expect? What happened between the rotor and the interface of the brake lining? Is it convective or conductive? There is a conductive, right. So, in this it is a convection heat transfer, here is convection heat transfer, and in this portion you will have a conductive, okay, conductive heat transfer. How about the interface of the brake lining and the support? What do you expect? That is also conductive, right, that is also you will have another conductive. So, another conductive will be there. Okay. Yeah. So, there is a heat transfer happening, this is for the pad and this is for the rotor. Anything else? So, of course, I had to give you thickness, since we are talking about the thickness of the rotor, half of the thickness L, and this is your I just want to redraw, okay, and no need to, I will just mark it here itself. Okay. This is your delta S support steel ds thickness and this is delta P. Okay. L is the half thickness of rotor, delta S thickness of the supporting plate, delta P thickness of the brake pad or brake lining pad. Yeah. Okay. We may ask question, why are you so concerned about these things? Why we concerned about the thickness? See, as I said earlier, we need to identify the sizing of your brake system. So far we did as a structural aspect, but as you are aware of that, the thermal stresses are very high compared to your mechanical stresses or structural stresses. So, in that case we need to have the optimum or designed surface and the thickness for enabling your heat transfer, right. So, or fixing the size of your drum or rotor including a brake lining. So, in fact, what we do, we can take it as a area. I will give you introduce some more thing. So, AR is the area of the rotor, okay, and HR heat transfer coefficient, of rotor, and of course the temperature will take it as a T room temperature, T infinity, okay. T infinity is the room temperature. Probably I will rewrite again in the next slides for better understanding. So, this is the pad. So, this is your rotor, sorry, then this is your pad, brake lining pad, and this is your thickness of your the support, right. So, already I have given this is the L, right. This will be delta P and this will be delta S. Then you have from here AR, HR and T infinity, so room temperature. Similar way you can have the pad aspect, the area of the pad, heat transfer for the pad and the temperature to infinity. Yeah, this is your pad and pad support. Okay. So, what are the thermal resistance you expect now for repeated braking? What are the thermal stresses you expect here in steady state condition? Okay. Can I need to find out the thermal resistance of the rotor. Tell me, how do you expect the thermal resistance of the rotor here? Is it going to be the convective heat transfer or conductive, or yeah, both? Are you sure? Look at this. So, you have, this is your drum, right? This is your rotor, assuming that, and this then you have a pad here. So, we are talking only this aspect, we are not talking the interface at the moment, we are talking only the rotor. So, what happened? You will only convective, right? I do not think so you will have heat conduction, only the convective heat transfer will take place. Okay. For steady state condition, so it will be sigma RR equal to 1 by HR and AR, right, 1 by HR. So, surface area already given, HR is the surface area, sorry, AR is the surface area of the rotor, HR is the heat transfer coefficient of the rotor, convective heat transfer. So, that is clearly given. Now, we will talking about the thermal resistance of at steady state for the brake pad. To tell me, what do you expect for pad here? What are the transfer you expect here, heat resistance you expect here? Look at the diagram. Okay. So, you have a conductive, one is conductive, right, that is clearly given, and you have a convective also, right, you have a conductive, convective, and also there is one more conductive between the pad as well as the pad support. The three resistance are involved there. Okay. So, convective resistance plus conduction resistance the conduction resistance between rotor and pad plus conduction resistance between pad and pad support. So, we have three things. So, we have the heat dissipation to convective, heat dissipation to the conductive between the your drum as well as the pad, and also conduction between the pad as well as support. So, all those things are there. So, in fact, I can simply write this one HP AP plus delta P by Kp AP, okay, plus delta S. These are the standard heat transfer. I am sure you would aware of these things, and this is what happened. The area surface area will be remain same, be it pad or pad support. Okay, so that can be as a P, whereas Ks is different. The thermal conductivity of the support is very different from the thermal conductivity of your pad, right. These are the three equation. So I need to find out the heat distribution factor for the rotor QR dF, right. If I want to QR by QP plus QR, of course rearrange 1 by 1 plus QP by QR, right. When you do that, it will be 1 by 1 plus, yeah, sigma RR, okay, and sigma RP. So already we have individually find out what will be thermal resistance of the pad, right, and also what is the thermal resistance of your rotor. When you substitute, finally you would expect the equation. So already we know, we have done that. So we are going to write the QR distribution factor dF equal to 1 by 1 plus HR AR divided by 1 by HP AP delta P by Kp AP plus delta S Ks AP. So this is what you are expecting, the heat distribution factor for the rotor, right. Similar way you can identify for the heat distribution factor for the pad also, right. I think I will stop now. Okay, we will continue the temperature analysis tomorrow lectures.